Finally, we come to first attempt to use replica method. Namely, we consider first solution of spin glass problem proposed by Sherrington and Kirkpatrick. So I will explain how how to average over disorder in a spin glass model, and what happens if you do it in a simplest way. It will be some solution, actually not correct, but it will contain some reasonable features. I think before we will discuss next week a better solution, it is useful to start from the simplest or not quite correct one. So, this is a Hamiltonian. Sigma, as usual, is plus minus 1. Couplings are random Gaussian distributed. And what we need is to find average free energy averaged over this distribution of couplings. Now, partition function is explicitly a sum over all configuration of sigma, as it is shown here. But we need to average free energy, which is a logarithm of partition function. Then what we will be looking for, actually. We will try to calculate a very unusual order parameter, which was introduced previously by Edwards and Anderson, who actually wrote this Hamiltonian. This was the beginning of theory of spin glasses. The method we used was not very successful, I would say. It was not the whole further development of the theory was in a different direction, but it was a kind of foundational paper, and the major point was to introduce what plays a role of the order parameter in spin glass theory. We discuss it from different point of view on a lecture about Thouless-Anderson-Palmer function. Here we have just the set of magnetizations, M average spins in each side, as a substitute for a simple order parameter. Not very convenient substitute because these Mi are all different in all locations. Now, the idea of Edwards and Anderson was to consider the simplest quantity, which is thermal average of each spin, sigma I, shown by these angular brackets. Of course, it is random, plus and minus. Now let us take square and average this square over the whole system. So it contains 3 steps, actually. What the solution proposed by Shenton and Kirkpatrick tries to avoid considering these complications. Just let's try to work with this Q Edwards-Anderson like it would be a simple order parameter. So let's look what happens.
Sorry, one question. Can you go back one slide, please? Like the overline is the average over disorder is the
Yeah, here,
especially, or they are the same in the end?
here it is assumed that averaging over disorder and averaging over system is equivalent.
Okay.
Yes. So, first point. Let us try to average over disorder logarithm of partition function. The way to do it is to write down formally logarithm as a limit of this z to power n minus 1 divided by n and n to 0 limit. Then, in order to calculate z in power n, we need to consider n replicas of the same system. This is why the term replica appears. So if z was the sum of all configuration of sigma I, then let us write just the product of n times of such a sums. So we have in each site, we have not a single sigma I, but n of them. Sigma I1, sigma I2, and so on. Then we can take the average, which is shown here. Gaussian average gives you this four order terms in sigma. And here in this sum, alpha replica indices, alpha, are not equal to beta, because if the terms with alpha equal to beta are trivial, because sigma squared is just 1. Mm-hmm. And that is taken care by this factor.
Sorry, one question. The replica tree, like a general question, the replica tree is there like an example of physical example when it fails when we cannot use it, or we can always, when we have the disorder quenched, we can also go on and use the replica tree?
Would it fail or not depends what you do next. If you, I don't know example where it would be found to fail just in principle. But the cost of this success to average over disorder from very beginning, the cost is that you have now system with n times more variables. And what is even more important, at the end, you need to put this n to 0. And this procedure is not trivial at all. You could imagine different ways to do it, and some of them, or most of them, will be incorrect. So you need to invent some correct way how to deal with it. Eventually, this is what Parisi did, and that I will discuss next week. So now we have this fourth order term in sigma, and we need to decouple it, a bit similar to what I have shown in the morning in dynamical theory. but here it is decoupling using this integration over q alpha beta, alpha not equal to beta, with this term n q alpha beta squared. So by integration, by doing this Gaussian integration, you exactly reproduce previous expression. Now, n is thermodynamically large, so you can use later on saddle point approximation with for integration over q. So we are looking for saddle point solution for this matrix q alpha beta. Now this object here, it contains, it is a free energy, which now refers to each side independently. Here you have only I, because coupling between I and J is already removed by this transformation. But you still have coupling between alpha and beta with this matrix. Now, saddle point equation is the following: that you take a variation over q and put it to 0, and it leads you to this equation, that q alpha beta is average over sigma alpha sigma beta. This averaging means you take a trace with such a Gibbs weight. Now, crucial point. Let us make assumption that all these elements q alpha beta with alpha different from beta, that they all are the same and equal to some number q small. Then here you put this q, which simplifies the whole story a lot. Still, you have here products of different sigma alpha and sigma beta. But you can avoid this mixing of different replicas by introducing additional Hubbard-Stratonovich field. It is not this integration is not written here explicitly, but here it is, Z. So you instead of considering this coupling sigma alpha sigma beta, you introduce another field which is coupled to sigma linearly. And what you need to keep to be correct is the variance of this field. So here you see q1/2, z, and the Gaussian weight. If you integrate over z, you will get just such coupling terms. Now, the self-consistency equation for Q matrix, if we make this assumption that all matrix elements are equal, it will become this equation. So we now can sum over all sigmas. Each summation gives you hyperbolic tangents with effective field, which is this combination, external field plus random field with a given variance. So this is finally our self-consistent solution for the quantity Q. If we put external field to 0 H, then we can easily find that there is a transition temperature such that above Tc, the only solution is Q equals 0. But below this Tc, it is actually again equal to J. Below this transition temperature, we find non-zero solution with Q proportional to tau plus tau squared over 3. Tau is this difference. So below Tc, this tau is a positive small number. Okay. Then we also need to eventually to calculate free energy and entropy of this solution. In order to do it, I mean, technically to go through this calculation, it is important to keep this term n multiplied by q, although eventually n will go to 0. But we need to keep it on intermediate steps, because I should mention that what we need to calculate is a limit of n to 0 of z to power n minus 1 and divided by n here. So in some expressions, this becomes important. Good. Now, once we made it, we can get a free energy for this Renton-Kirkpatrick solution. It is given by this simple expression. You may remember the first term reminds you what we have seen in Taulis-Anderson-Palmer solution. It is a correlation energy. And the second part presents you the entropic part. This entropy of a spin which is sitting in a random field with variance Q, Z, J, and possibly also with external field H. When close to Tc, free energy per spin is given by this expression. You can recognize here again this tau cube term, which we already found in Taulis-Anderson-Palmer approach. So this term appears for below Tc. So it is not a second order transition, but it could be called third order transition because third derivative of free energy has a singularity. And again, free energy below Tc is larger than a trivial solution, as I already mentioned before. Now, this term with H can be used to calculate magnetic susceptibility. Second derivative of free energy over magnetic field. The solution we found corresponds to the dashed line below transition temperature. I already mentioned that, in fact, susceptibility below transition temperature depends on the procedure. Either we could cool the system and then apply magnetic field and measure magnetization, or we apply magnetic field, cool, and then the same. And the results are different. Field cooled magnetization corresponds on this plot to a full line. Within Sherrington-Kirkpatrick solution, we do not obtain this field cooled magnetization. The only thing we obtain is this zero field cooled solution shown by broken line. Now, in order to get this field cooled susceptibility, it is absolutely necessary to use more advanced approach with breaking of replica symmetries between replicas. That we will discuss next time. Now, important point. We know from Thouless-Anderson-Palmer analysis that this solution, this equality is valid everywhere in the low temperature phase. By the way, this Thouless-Anderson-Palmer paper come 2 years later than Sherrington-Kirkpatrick. So, but when Sherrington-Kirkpatrick developed this theory, this was not known yet. But now we can compare. And what we see is that this marginal stability condition is not fulfilled by Sherrington-Kirkpatrick solution. We calculate left-hand side and right-hand side using this QSK is tau plus tau squared by 3 or minus 1/3 was definitely there. Up and no, here plus. So the coefficient, one thing is correct, that order parameter is proportional to T minus Tc, is tau, with correct coefficient. But the next term is not correct. And we see it by comparing left-hand side, right-hand side of this marginal stability equation. We see that there is some mismatch. Now, even worse thing. Let us consider a solution of self-consistency equation in zero temperature limit. And we put magnetic field to 0. Then this equation in zero temperature limit gives us solution with Q approaching 1 with corrections linear in temperature. Now we can use this solution and calculate free energy in the same limit. The result is that at low temperatures, the energy per spin is this, T over 2 pi, which is nonsense because it is equivalent to negative entropy. So something is definitely wrong. I should say that this very rough point that entropy becomes negative, it happens only at sufficiently low temperatures. Close to transition temperature, entropy is something at least positive. So you don't see immediately that this solution is incorrect from entropy. But there is another way to see what happens. And let me discuss it from two different perspectives. What we learn, what we learn later on, the physical, important physical point about spin glass is that there is no unique solution for distribution of magnetizations. There is a large set of solutions, each of them correspond to extremum, even local minimum. But there is an exponentially large number of them, as I mentioned on the lecture about Thouless-Anderson-Palmer equations. So you can find a system in one of many metastable states, which are denoted here by letter A, B, and so on. And there is no transition between these different metastable states because energy barriers which separate these solutions are thermodynamically large. So then within Sheraton-Kirkpatrick solution, this feature is not taken into account. We work with it like it would be a single state. Actually, the Edwards-Anderson order parameter, if we average it over possible different metastable states, we need to find this mi for each of this state, take its square, and then weight it with probability to find our system in different metastable states. On the other hand, there is another way to average, namely to take into account explicitly that many different configurations may exist. And then we can define another order parameter like this. They don't need to be the same. So there is a problem. What is actually the order parameter? And the resolution to this puzzle is that in a spin glass you cannot use order parameter as just a number. What we will see next time is that the correct order parameter, if we work in a replica theory, is not a number but a function. Function like q is a function of some variable x with x defined between 0 and 1. Yeah.
Just to make sure that is correct. When you refer to metastable states, you mean that when we do our minimization, we assume that we have this replicate symmetry.
Mm-hmm. This is what we inserted by hand.
Yes, exactly. So those were only taking into account only one minimum. And all other metastable states, they correspond to other configurations of this Q alpha beta, which are not symmetric at all. But
no, it is not so. It is not so direct. It is not so direct. It is a bit more complicated. I mean that the description in terms of a order parameter as a single number by itself assumes that there is only one state, maybe up to overall inversion, only one state in which we come when we cool the system. But in fact, we can find a system in a many different states, very large number of them, which are not related by any symmetry. And this feature is not captured by attempt to describe order parameter via single number. Now, a formal proof. This Sherrington-Kirkpatrick solution is unstable with respect to some fluctuations. So we assume that there is a solution Q alpha beta equal to Q small. Now let us add some Q alpha beta small as fluctuations near this solution. And look for the eigenvalues of a quadratic form associated with this Q alpha beta. Then we can show that free energy is saddle point free energy, and this additional term here, alpha, beta, gamma, delta, all different indices. And we need to calculate two averages, all four together, and then to subtract this. Okay, this we need to take average with the same Hamiltonian. Now, there are three different types of quadratic terms in terms of this Q alpha beta. 1, 2, 3. The point is that while this C1 and C2 are does not change sign when temperature crosses Tc, this term changes sign. So, of course, we understand that at T above Tc, everything is stable. And first of all, trivial state with zero order parameter is stable thermodynamically. Now we see that this coefficient 2t squared minus c naught change sign. And it means that our solution with a constant q is unstable with respect to some vector in this matrix and replica space. So just exactly these fluctuations diverge because the coefficient in front of quadratic term is negative. It tells us that the solution cannot be correct, although it gives in the main order in T minus Tc, it gives a reasonable answer, but it is not stable and should be somehow corrected. By the way, let us make some small step back and discuss what is the behavior of these fluctuations in above Tc. We can define two types of correlation functions, which can be averaged over disorder and to give some non-zero result. Here, this is usual correlation function, irreducible correlation function of two spins. This double brackets means irreducible correlation function. In order to get something non-zero, we need to square it and average. Another correlation function is this K. It is an irreducible correlation function of S squared. Actually, it is this quantity which determines the non-linear response to magnetic field. Now, above Tc, we are related by a very simple formula like this. If we write down all these terms in irreducible correlation function, yeah.
So the average is
Over line. Yes, here this bar on the top means averaging. No, look, this, for example, Si squared, Sj squared, irreducible correlation function. It means we take Si squared, Sj squared average minus Si squared average, Sj squared average minus 2 SI Sj. These two cancel each other because it is 1 and this is 1. And the rest is just minus 2 of this J. And to calculate this J, we need to write just a LAD diagram. Here, of course, again, for large infinite range limit or a large nearest number of nearest neighbors. The major diagram is a ladder, and to get it squared, you need to write down another ladder and average. And the result will be usual Einstein-Czerny correlation function, but for unusual objects. And K is also singular and negative. And it reminds us what I was telling you in the first lecture, that once when you consider magnetization as function of external field, you have something like cusp, like T, Tc, something like this. But as long as you increase magnetic field, this cusp becomes rounded and more rounded. This is just nonlinear susceptibility, and it is singular around this point. So just in correspondence to this formula. But okay, now now we till now I discussed mainly the situation without external field. So we found that this solution of Sherrington-Kirkpatrick, this in principle gives us non-zero order parameter, but it is unstable. Now let us consider the more general case when external field is present. It enters only together with this random field. So first thing to check, we already know that there is a marginal stability condition. Let us check when this condition is fulfilled or not in presence of external field, magnetic field. Then this 1 over m squared average is nothing but cosinus effective field by temperature for rising speed. And we need to, this effective field is random. Okay, but in the marginal stability condition, we have this thing squared. So it will be hyperbolic cosine in power 4. We need to average it over z. Then the result is that if external field is weak, like this, the temperature such that this condition is violated is given by this formula. Let me draw it here. Temperature field, that will be Tc, and 2/3. So will be something like this. H. This critical line was found by De Almeida and Taulis and so-called AT line. We can consider the same equation at a strong magnetic field. And here we have also some non-zero value of temperature, but low value. There again, this instability happens. So it will go like this. It might be strange that even when magnetic field is much larger than variance of our coupling, still we, at low temperature, we have some kind of instability. But there is a rather simple qualitative argument why it happens like this. The point is that we assume that our matrix elements J, Jij, that they are distributed with Gaussian distribution, which means that with some low probability we can find even very large matrix elements. Now, let us consider the probability that external field is large, is much larger than J and T. But let us estimate the fraction of spins in the system, which fill a very small total field. Total field is the sum of H plus this J, Ij, sigma J. Then, since this sum with a Gaussian probability can reach any large value, there is a fraction of all spins. This rho is a fraction, n is a total number of spins. So there is a fraction of spins like this, which have overall field acting on them small. and they still interact via the same coupling. So this fraction decreases with temperature, and the condition for this instability is just this. So at very large field, only small proportion of all spins do not know where to go, plus or minus. But there is some non-zero fraction, and that is enough to lead to the same effect, to multiplicity of minima. So this is a general phase diagram in terms of temperature divided by coupling, J, and also here introduce average value of coupling matrix elements, J naught, which was 0 previously. But we can introduce it in and get it through all these equations. Then what do we have? Paramagnetic phase and spin glass phase here at low temperatures. And then some new phases appear here when average value of matrix element is larger than dispersion. Here we may have two different additional phases. One is a ferromagnet, then randomness in this J is not relevant, at least qualitatively. And another one is a mixture, ferromagnet plus spin glass. What is this mixture? It means that on one hand side, there is some average magnetization, average thermodynamic, and then average over the system, over the whole volume, or average over the zone. It will be some non-zero average magnetization. But why it is spin glass? Because it has multiple solutions. It is not just a ferromagnet with some small alternations, but there are many different solutions. All of them have some non-zero average magnetization, but the solutions are different. And the same story with a breakdown of replica symmetric solution is valid here as well. Yeah?
What happens if you go with the negative logistic? Is it synthetic with antiferromagnet instead of ferromagnet?
No, because we consider infinite range model, and for infinite range model it is difficult to define what is antiferromagnet. If it would be, say, cubic lattice, then of course you can switch notation and it would be equivalent. But here we discuss this infinite range, and antiferromagnet is not clear what it is. So what are the major problems of the solution we found? The good thing is that we found that this mi squared average q is proportional to tau, it is positive. That's okay. Bad sides are there is no account for any history dependence of the state, which is important for spin glasses. For the same reason, I will always discuss this Ising problem, but we could discuss a basically similar problem like which I called gauge glass. It is, if you would write a Hamiltonian like I, J, J, I, J, e to I, phi minus phi j. Plus Hermitian conjugated. And phi is a phase variable on a circle. This is actually the model of Josephson array. And then this J are just Josephson coupling energies. In particular, it was an interesting model in the beginning of the discovery of high TC superconductors in 87. Because, do you know what is high TC superconductor? So originally, people were able to produce these materials, rather complicated materials, in the form of ceramics, made out of some small grains. And these grains are coupled via tunnel barriers. Then this is natural description of the system. Now, if you introduce an additional external magnetic field, then this J becomes J modulus, and here some phase, random phases, which comes from vector potential of magnetic field. If magnetic field is sufficiently strong, you have with matrix elements just Hermitian random matrix. This model is can be treated in a way rather similar to what we discussed for Ising spins. With the difference just that instead of real random matrix, we have Hermitian random matrix, and variable is not spin plus minus 1, but this complex number with unit magnitude. Technically, it is rather similar. Physically, what it means. We can ask the question, suppose we cool our Josephson array in some magnetic field, and then change this magnetic field. Change magnetic field means we come from one realization of these couplings to another one with completely different statistical properties. It is different realization, but the difference is that we just change some phases here and there. The question, will we have some diamagnetic response in such a system? So, does it behave as a superconductor in any sense? Because superconductor should provide you with diamagnetic response. In fact, I mean, experiment shows that yes, it is diamagnetic superconductor with diamagnetic response. Although it is not a classical superconductor in the sense that there is no Meissner effect. Magnetic field is not pushed out of such system, but it is frozen inside. Now, if we treat this system in the way like with Sherrington-Kirkpatrick theory, unfortunately, we would not get any diamagnetic response. It would be zero. just because this approximation cannot treat history dependence. It is when I say we change magnetic field, I could also change magnetic field at high temperature and cool the system. I will get some state which is not in statistical properties. It is not different from another one. Whatever strong magnetic field I will use, it will be statistically the same system with the same average properties. So on the plane TH, I can go to this point, measure average magnetization. It will be 0. But I can come to the same point by another path, like this. Cool, and then change magnetic field. And it will lead to magnetization. Just because this glassy system, it would have a lowest energy state, which we find going at finite magnetic field down. That would be the lowest energy state. But when we do it like this, there are no process which can transform the original state corresponding to this field to the most lowest energy one, because the system becomes non-ergodic. It is frozen in some set of configurations which do not include this one. I?
You need an external field to go there and recall the ergodicity.
No, to recall ergodicity, I would need to go out of this glassy phase. So, I mean, it would be here it would be glassy phase, boundary, which looks somehow like this. So I would need to go back and then cool again. So this is the trick of non-ergodicity. Okay. So that's it for today. Any additional questions? Good.
Thank you.
Thank you.